All right, so on the next page, we're going to take a look at the same idea of special cases, just showing kind of what they look like whenever you encounter them while using the elimination or addition process. So with these two, we, again, for elimination, want to look at the x's or the y's, and we want the coefficients to be the same number but opposite sign. So again, that idea of like the LCD essentially. What number do 3 and 6 both go into? Well, it'd be 6. Or what number do 2 and 4 go into? It would be 4. And then, again, keeping in mind the idea that you want one positive and one negative, we need to figure out what it is we would do to one or both of these equations to get those coefficients to match up with same number but opposite sign. So it turns out that whichever one you choose, whether you say let's eliminate x or y, let's just say we're going to go with the x's. We see a positive 3 and a negative 6. To get those to be the same number but opposite sign, we can take a 3 and change it to a 6 by multiplying by a 2. And that's all it takes. We multiply this top equation by a 2. This will be a 6x. This we will keep the same as a negative 6x, and we'll be good to go. But as we do that, we get a 6x and a minus 4y equals 20, leaving the second equation unchanged. Gives us that. And then as we go to take the elimination or the addition step, notice that these cancel each other out, kind of, I'll say like we were planning, but something that didn't happen before with the elimination process is that your other variables cancel out as well, leaving you with nothing here on the left side. Now on the right side, we've got 20 and a negative 20, so just so happens those cancel each other out as well. So not only have we gotten to this point, I'll put that star there again, like on the other page, where the variable, or in this case, variables, have disappeared. Right? There are no more variables in this equation. So you look at the statement. Now the statement says 0 equals 0. And so I would say this qualifies as an always true statement. Right? That is correct. So just like with the other process, when you get to this stage, if you're left with a statement that is always true, that means that these two equations are the same equation. They're the same graph of the same line. They're going to share all those points in common. So again, that 3-word phrase that we will use is infinitely many solutions. And that's it. Moving on to the other example in your notes here. Same idea. We already have the x's and y's equals constants lined up. And so the goal is for the x's or the y's, same number but opposite sign. So we're going to need to do some kind of manipulation here. Whether we want 2 and 4 to both be 4x or 1 and 2 to both be 2y, notice we will need to worry about a change in sign because right now they're both positive, both the same. So if we take this top equation and multiply it by, well, again, whichever one you look at, because of this special case we're dealing with, it's going to be a negative 2, right? 2 times 2 would give me a 4, but I'm going to need a negative to turn this to a negative 4 if I leave that a positive 4. So to multiply that top equation by a negative 2 would give me negative 4x minus 2y, and that would be a negative 26. Leaving the second equation alone, not changing it at all. Just recopying it there, and then going through the elimination or the addition step. There go our x's, and again, there go our y's, leaving us still nothing on the left. On the right, negative 26 and 23 do give us a negative 3. And so what we have is, again, variables gone. Variables disappear, but that statement there, that is now a statement that is not true. Right? 0 does not equal negative 3. So since this doesn't make sense, that would be us saying that this original system doesn't have an answer. So that's our 2-word phrase for a special case of no solution.